One of the useful things which we can do with our knowledge of matrices is we can put them to work in solving systems of linear equations. And the reason this is so useful is that systems of linear equations tend to arise in all kinds of areas of mathematics and all kinds of applications of mathematics. So let's begin by saying exactly what we mean by a system of linear equations. A system of m linear equations in n variables, the variables are going to be called x1 up to xn, is a list of simultaneous equations. So we have here m simultaneous equations, and here the numbers a11, a12, and in general aij are just numbers. They're the coefficients on the left-hand side of the equations, and the bi equally are numbers. They're numbers appearing on the right-hand side. Now we can write this system of linear equations in matrix form, and the matrix form of such a system is ax is equal to b, where A is the matrix, so the m by n matrix, whose entries are the coefficients on the left-hand side of those equations. B is the matrix of the coefficients appearing on the right-hand side of these equations, and x is a column vector consisting of the variables. And you can see that what you've got on the left-hand side is exactly the entries of the matrix product A times B. So saying that AX is equal to B is exactly equivalent to saying that these simultaneous equations are all true. So let's just do a quick example of doing a system of linear equations. Let's say you had a system like, I don't know, x minus 2y plus z is equal to 7, and y plus 2z is equal to 13. Well, then the matrix form of this would be, well, your matrix A would be the matrix which is the coefficients on the left, so not the variables, just the coefficients. So that's 1 minus 2, 1, and then 0 x's and 1 y and 2 z's, and then your variables were x and y and z in this case, and then the right hand side, the b, would be the column vector of height 2 with entries 7 and 13. So in this way we can represent systems of linear equations in a matrix form and then use our matrix methods to study them. So let's make an observation which we can do already, which is just using the things we learned about invertibility, which is that if A is invertible, then the matrix equation Ax equals B has one and only one solution. And that's quite special because in general a system of linear equations might have no solutions at all, or it might have just one solution, like in this case, or it might have infinitely many cases. So let's just see why this is true. Well, the reason is if you've got any solution, so a solution is a column vector u such that A times u is really equal to B, well then you could multiply both sides on the left by A inverse. So A inverse AU is equal to A inverse B. But of course A inverse times A is just the identity matrix. And of course multiplying by the identity doesn't do anything, so you just get U again. Okay, so A inverse times B is the only solution to that system of matrix, that system of linear equations, or that matrix equation. In general, your coefficient matrix A might not even be square, let alone be invertible, so many more complicated things might happen. But in this particular case, you can see that there is a unique solution to this system of linear equations. All right, so let's ask the question now, when does a matrix equation Ax equals B have a solution? And what I mean by that is for which possible B's is there a solution? So in general, for some values of B there will be a solution, for some values of B there won't be any solutions. So we'd like to ask the question, what can we say about the vectors B for which Ax equals B have a solution? Now we know something about how multiplying a matrix into a column vector works, because we learned this in video 2 about matrix multiplication. So specifically, if you give names to the columns of A, so if we write the first column, if we call that C1, the second column C2, and then the nth column, the last column Cn, and if we let U be a column vector, so U1 down to Un, then you know that if you do the matrix multiplication A times U, the result is u1 times the first column of A plus u2 times the second column, and so on up to un times the last column. And we called an expression like this a linear combination of the columns of A. So every vector which we can write as A times u is equal to a linear combination of the columns of A. So the only values of B for which there would be a solution are those values of B which are linear combinations of the columns of A. So that means that this set of linear combinations of the columns is special, it's important to us. So we're going to give it a name. We're going to call it the column space of A, and we're going to write it as C of A like this. So here's the formal definition. If you've got a matrix A, the column space of A, which we write like this, C of A, is equal to the set of all linear combinations of the columns of A. In other words, all the vectors of the form a scalar times C1 plus a scalar times C2 plus a scalar times C3, and so on up to a scalar times Cn, where what I've written here is u1 up to un can be any element, any real number each time. So actually let me comment that sometimes we might be interested in complex vectors as well. So if we work with complex vectors or complex matrices, instead the complex numbers instead of the real numbers. But in general, for most of Math 5, we'll only think about real vectors and real scalars. Okay, so we've made this definition precisely because it allows us to say that the matrix equation AX equals B has a solution if and only if B belongs to this column space of A. The column space is something we're going to revisit. It's going to be an example of what's going to be called a subspace of R to the M, and we're going to learn all about subspaces in the final chapter of Math 5. But for now, we've introduced this column space with the purpose of being able to say that the matrix equation AX equals B then has a solution if and only if B belongs to the column space of A. So let's now think about a special kind of linear system. So the special kind of linear system we're going to think about, or the special kind of matrix equation, is the one where the right-hand side, so the B in the language of the previous slide, is 0. A homogeneous matrix equation then is one of the form AX is equal to 0. And you'll notice that these always have a solution. They always have a solution because the 0 vector is a solution. And the reason to study these is because you can express the solutions of any matrix equation, so not just a homogeneous one, in terms of the solutions to the corresponding homogeneous problem in the following sense. So let's say you've somehow found just one solution, we'll call it P, to a matrix equation AX equals B. Then every other solution of AX equals B can be written as P plus a solution to the homogeneous equation AX equals 0. So that means if we've got a method for solving the homogeneous equation, then once we do that, then if you can find just one solution to an inhomogeneous equation, then you can find all of the other solutions just by saying that they are equal to that particular solution plus any element or any solution to the homogeneous equation. So let's see why this is true. So we'll let Q be any solution to AX equals B. Then if you think what happens to A times Q minus P, what do I get when I do this? Well, I know there are some rules which allow me to just multiply this out and say that this is A times Q minus A times P. We looked at the properties of matrix multiplication, and that was one of them. So what I've got there is just B minus B, because that P and Q are both solutions to AX equals B. So this is 0. So the vector K, which I'm going to define to be Q minus P, is a solution to AX equals 0, and Q is equal to P plus K. All right, so if you somehow found one particular solution to your matrix equation AX equals B, then every other solution is equal to that particular solution plus some solution to the homogeneous problem AX equals 0. So solving those homogeneous problems is going to be particularly important to us. And it's so important that the set of solutions to this equation, to this homogeneous equation, gets a special name. It's called the null space of A, and it's written as n of A like this. So that is the set of all solutions to AX equals 0. And again, this is going to be an example of what's called a subspace, and we will meet subspaces in the final chapter of Math 5.